Mark Glickman, and I'm at Harvard University as a senior lecturer in statistics.
Well, statistics is a topic that the audience really loves hearing about. Before we get into the main topic, can you give us a little bit of background on the areas of stats that you've studied, or maybe those that interest you the most?
Yeah, well, what got me into statistics in the first place actually was my interest in the game chess. I've always been interested in how chess players get rated when they play in tournaments. In other words, when you go to a tournament, you get a numerical rating where if you have two players that have ratings, you can actually determine the probability that one player defeats another. And that was something that I was always interested in, these chess rating systems. And I ended up getting really into statistics and the mathematical aspects of these kinds of systems. And I developed a couple systems that are in use these days, especially in online gaming. It's called the Glico system. So that's what really got me into statistics in the first place. And then, I really have a passion for teaching. So that's a big part of my statistics life. And then much more recently, I got into the intersection between statistics and music. And this Beatles Authorship Attribution project is one of the bits of work. I also got involved with a student who was really the primary driver of this work on basically how do you statistically generate music that sounds like Bach chorales. And so we have a paper that's going to be coming out very shortly in that area. So music's become a much bigger focus in my statistics life these days.
Is there anything, obviously interest could drive it, but I'm curious if there's any computational component to it, maybe the availability of computers to run big simulations and that sort of thing. Has that influenced the ability to ask interesting questions along these lines?
Yeah, generally it helps. I tend not to gravitate to problems which can only be solved by having the appropriate hardware to be able to crank through the data. But, having access to good computing definitely makes a big difference.
I think we can take for granted that any listener must be aware of the Beatles and their influence on music, regardless of what they like. I'm sure they could hum a few, but tell us a little bit more background for those that don't know the discography. What were the types of problems you were looking to approach?
This whole project essentially started when I met my main collaborator for this project, Jason Brown, when the two of us happened to be at this conference in Prince Edward Island. We just happened to be talking after I gave a talk on some material actually that's related to rating systems for chess players. And we just happened to stumble on our mutual interest in music and in the Beatles. And he was telling me that he had gained a little bit of infamy about 15 years ago, where he used essentially Fourier analysis, decomposing the sounds from the starting chord of A Hard Day's Night to figure out the actual instrumentation of the chord, because that apparently been something that was in pretty serious dispute. So he published a little article on it, and that got him some attention. And he was telling me since then, one of the things that he was particularly interested in was being able to represent songs, particularly Beatles songs, in a particular format in his area of math, which is graph theory. So essentially representing music in the form of essentially graphs or networks. And he wanted to ultimately be able to use it to be able to distinguish authorship of different Beatles songs. Like maybe there'd be stylistic differences that would be evident in these representations. And he wasn't really making a lot of headway. And the whole problem of being able to distinguish authorship is something that's much more firmly in the wheelhouse of a statistician. So, I told him it sounds like really interesting problem. It's something I would want to be heavily involved in. And so we ended up starting this collaboration. And that was kind of the start of it all. So we tried lots of different sorts of things to take the music and be able to figure out how can you predict authorship from musical features. And that's essentially what led us down the path to the work that eventually got published.
So from my perspective, wearing my data scientist hat, I would say you have a fixed data set that is partially labeled. Does that feel like the right framing for you?
The main question of interest, really, just to take a step back, is that there are a handful of songs by the Beatles. And again, there's nothing about this problem that has to be specific to the Beatles. But for our interest, there are a handful of songs by the Beatles that are of disputed authorship. And so the idea is that you start off with a data set where the labels, which is to say the authorship of Lennon-McCartney songs, is known. And that's known because the Beatles, based on interviews and various information that's been gathered over the years, is of known authorship. So we have a data set where the labels are known. And then in addition to that, we have for all of those songs, we have a whole bunch of features. We have a whole bunch of information about various musical aspects of the songs. And the idea is to form a statistical model that uses those features to predict the labels. And then once you establish that relationship, then you apply it to the songs of disputed authorship to see what the prediction is going to be based on that relationship.
So for non-composers who might be listening, perhaps they could be intimidated by this problem, saying music is all about creativity and unpredictability and these sorts of things. Is this truly a solvable problem from that point of view?
Well, yeah, solvable is kind of a loaded word. I mean, we certainly made our best attempt. And by best, I basically mean after making lots of attempts that were not terribly predictive, we finally stumbled on a set of features and a statistical approach that seems to do a pretty reasonable job at making predictions. The simple answer, I suppose, is yes, it's possible, it's solvable in the sense that there is information that you can extract that is predictive of authorship. I could be pretty concrete about this. One thing that we knew before going into this work, and this is something that has been well known by musicologists studying Beatles music, which is that Paul McCartney songs in particular tend to have melodies that tend to move around a lot. Like Paul McCartney had a musical vocal range fairly wide, and part of that tended to be reflected in his moving melody. By contrast, John Lennon, who still had a reasonable vocal range, tended to write melodies that didn't move around very much. Like he used a lot of repeated notes, or the vocal movements would stay very close in pitch. And that's pretty characteristic of a lot of John Lennon songs. And so we knew even going into this problem that, musicologists have identified differences in the way that each of these songwriters would write music. So we knew that there were features that could be quantified and picked up and used as distinguishers in these classification models.
Yeah, I'd love to delve into those features a bit. Earlier, you'd mentioned the Fft analysis, and those are features, although I don't know if they're going to help with authorship per se, maybe. There's also linguistical features, these musicology things you've been mentioning, maybe even vocal choices. How do you figure out what's going to be useful and what's not in that sort of line of work?
That's really the main issue in this whole idea. I mean, there are tons of different ways that one could approach this kind of problem. And frankly, the best type of approach would be just to take the audio signal and then just analyze it and then pick out the features that are relevant that could be used in some kind of data science model. What we did was something very crude in a way. What we did was we restricted ourselves only to examining the melody line, essentially the pitches that were sung by the singer of the song, and the chord progression. So those are the only two features that we allowed to include. And part of the reason for doing that is in thinking through how we might apply this more generally across pop music, we wanted to really use the features that were sort of the least common denominator. Like we didn't want to use features that might differ quite a bit across different musicians and groups. So for example, one could imagine, for example, like whether a song is using a particular type of guitar sound or whether a song has like a horn section in it. That might be fine for a particular group, but then that might not apply very well to groups that just simply don't use brass instruments. So we kept it very simple in that sense. So we only ended up using just the chords and the melodic lines, just the pitches. And then based on that information, then we had to further distill the information into a whole bunch of features that essentially had some way of characterizing the song. So the kinds of things that we ended up extracting were things like whether the dominant chord was played, or whether the minor third was played at some point during the song, or whether there were certain chord transitions that occurred, or whether there were certain melodic transitions, or whether there were certain like contours, like whether there were sequences of notes that had pitches that went up followed by down followed by up. So that was the type of information that we extracted in developing the statistical model. So it's very crude information, but that's the approach that we ultimately ended up taking.
And in terms of that feature engineering process, is that a hand labeling system, or can you automate some of that?
So we did automate it. The pipeline for this project basically involved my collaborator, Jason, who mostly wrote out the melodic lines and the chord progressions with the aid of a lot of these musical scores that are produced for Beatles songs. Then we gave it to our third collaborator, who was a former student of mine, Ryan, who converted that information into essentially a big rectangular file, which consisted of each row of that file would be an individual song with a known label. And then the columns in that file would be each of the features that we ended up deciding were going to be potentially relevant. So once we had this big rectangular file, then I took it over and then I started playing around with all these different crazy statistical algorithms to be able to make predictive inferences about the songs.
And those chord progressions, it occurs to me we can draw a bit of an analogy to chess here, that in some games, there's 1,000 moves you could take. In other situations, there's probably one or two good moves that you want to use. A lot of musicians will be familiar with the 1-5-4-5 sort of progression. Sometimes there are obvious obvious choices in music. How can your techniques be robust to that?
Right. Well, one of the decisions that we figured out early on is that we don't want to so much like count the occurrences of certain features, but we want to just simply acknowledge whether a feature existed in a song or it simply didn't. And so it may very well be that maybe going from like the 1 chord to the 5 chord is so common that both McCartney and Lennon songs share that particular chord change in like most of their songs. But that's okay, because then we would end up concluding, based on the analysis that we do, that that particular feature is not a relevant feature for distinguishing the authorship. So the hope is that if we include sufficiently large number of features, then we'll be able to figure out which of them is truly distinguishing in the songwriting style. And, fortunately, this whole approach was able to distinguish a bunch of features.
Yeah, I'd love to go into, I don't know if you looked at it from like a feature importance point of view or whatever, but if we were to look at this from like a model interpretability point of view, can you look at those features and how they're used and kind of give a layperson's definition of what the model is doing?
For the layperson, the way to understand the results of this model is that there are a whole bunch of different musical features of each of these songs. And if a feature is in the song, that might kind of push the dial towards it being McCartney, or it might push the dial towards it being a Lennon feature. So just as an example, there's a particular melodic transition that occurs that can identify in any song, and that's the melodic transition from what's considered to be the flat third to the tonic. And for a non-musician, that tends to be a very bluesy sounding move. And that's actually something which, when it occurs in the song, it really moves the dial towards it being a McCartney song. Like Lennon did not use that melodic feature very much. So if that feature occurs, then it turns the dial more towards McCartney. But like in contrast, say, for example, like a movement in the melody that goes like one note up on the scale. So just basically starting from one note and then moving up a note very close to that original note. If that occurs in the song somewhere, that'll move the dial towards it being a John Lennon song. What ends up being something like 25 features or so that basically light up. And some of them tend to move more in the direction of the song being McCartney. Some move more in the direction of being Lennon. And then in aggregate, you kind of add up the different numerical values that are attached to each of these features, and then you get kind of an overall number. And that number can be converted into a probability that has a meaning of whether the song that you're applying our model to is likely to be a Lennon song or a McCartney song.
Thanks to this week's sponsor, the Springboard Data Science Career Track. The Data Science Career Track is similar to online boot camps, but the real difference is that it's project-based. So while you're learning methodology, you're applying it and building up your portfolio. That's key. Every open position for data scientist or similar engineer, I expect a GitHub link with something on it. Every student in the program is paired with a data science expert who provides unlimited one-on-one mentorship to support your unique needs. You'll need a basic understanding of Python or another modern object-oriented programming language, and some probability and statistics. And best of all, Springboard offers a job guarantee for all their career tracks. This means you don't have to pay for the program until you secure a job in the data science space. Data Skeptic listeners have access to an exclusive offer. There are scholarships of up to $500 for eligible applicants. Make sure to enter the code DATASPRINGBOARD, all caps, no spaces, when you enroll at springboard.com. There are 20 scholarships available for students who enroll. See how to qualify and apply. It takes just 10 minutes. Take the next step in your data science career. Head over to springboard.com, and it's Data Springboard for the code. And I imagine, as you'd mentioned, some of the musicologists will find some of those features to be of no surprise, things they already understood. Were there any features that were relevant that perhaps the musicologists didn't discover on their own?
Yeah, I mean, there's some features we kind of expected, like this last one that I mentioned about like a move of just a single note on the scale. That wasn't a big surprise, that being a Lennon-like feature, because we already knew that Lennon's vocal movements tended to be pretty restricted. It's not that surprising that Lennon tended to use more restricted movements in his melodies, as evidenced by single notes. But the kinds of things that were a little bit more interesting were, for example, a couple different chord changes. So just as an example, there's a chord change that goes from the major 4 to the minor 2nd. And for a non-musician, that just sounds like one big question mark. But it turns out that particular chord change, which turns out to be a change that's associated with McCartney, is one that is a fairly recognizable sort of chord movement, but it plays a very subtle role in the context of a song in a particular key. It actually, for musicians, it corresponds to a very natural chord change, which turns out to be going from the tonic to the minor sixth, but it does that in a modulated key. And that's one of the things that is quite subtle about Paul McCartney in his songwriting. There are some chord changes that are not like sort of obvious to detect if you weren't doing this kind of statistical analysis.
I'd love to touch on those statistical techniques. We left it off where you had this beautiful tabular data set, and I can think of 1,000 directions to run in, and I'm not sure which way to go. Where did you head?
Some of our initial approaches, which I'll mention super quickly, were to do things like using multinomial models on the existence of features and make that a function of the authorship, and then flip that relationship around using Bayes' rule in order to get a probability of authorship given the features. That was our initial approach, and it turned out that particular method tended to overfit the data too much. So we ended up backtracking, and the model we used was a fairly common model, so it's called Logistic Regression. And in a way, we were sort of disappointed that was our final model. We were trying a lot of things that were much more complex than logistic regression models, but it turns out that if you want to be careful about preventing overfitting, you have to end up using fairly rigid sorts of approaches and not machine learning approaches. I mean, I can't begin to tell you all of the different machine learning approaches that we tried. And the more flexible the approaches, like whether they were random forest approaches, which is something we've tried, or a variety of other machine learning approaches, these approaches tended to overfit. They were really good in fitting on the training data, but they were terrible when we were like withholding portions of the data and then seeing how well they fit on the left out samples. But we were super careful about overfitting. And the upshot is that we ended up using logistic regression, but the way that we ended up running our logistic regression was not standard. We ended up performing a sequence of 2 steps. The first step is something called sure independent screening, which basically means take each of the features and then one at a time check to see whether or not they're statistically significantly related to the authorship, and using a fairly permissive criteria that allowed the variable to get through. But if it seemed like complete randomness, then we would toss that feature. So that was the first step. So we started actually with 137 features. And if memory serves me correctly, I think that screening process ended up bringing the number of features down to about 40 or 50. Once we were at that point, then we performed something called elastic net regularized logistic regression. And so it's a particular way of running logistic regression that basically is a good way to prevent overfitting using some techniques that prevent the coefficients in the logistic regression from getting too far away from zero, which is actually a good thing. And there's some other little details in there, which I'm not describing, that involve being protected through cross-validation. But the upshot is that the final model turned out to be just an ordinary logistic regression model, but it just estimated in this kind of kooky way.
So then one of the advantages of logistic regression is you get to see the feature importance weights that the algorithm came up with. And we've talked a little bit already about what some of those features are. Would you mind sharing some details on the distribution? Like, is most of the predictive power in the top 3, or is it more spread out?
It's fairly spread out. So these are all coefficients in a logistic regression model that each multiply a binary predictor. So in a way, it's easy to understand, roughly speaking, how to interpret these coefficients. So just as an example, sort of a typical value of a coefficient in our model might be hovering around in the magnitude of like 0.3, 0.4. So just as an example, a transition from the 4th on a diatonic scale to the flat 3rd turns out to be an additive coefficient of 0.48, which basically means that if in a song there was a transition from the 4th to the flat 3rd, then you would end up getting this additive contribution of 0.48, which turns out to be this additive contribution in the direction of Paul McCartney. And then by contrast, if you have a move from the tonic to the minor 6, that would be a subtraction of 0.3, which would be a move in the direction of John Lennon. So you would take all of these different coefficients, as you normally would for logistic regression, and you would add up all of the coefficients that correspond to Lennon moves or McCartney moves. And what you get at the end of it all is a number that you would convert using the so-called inverse logit function, and that'll give you a probability. And that's going to be a probability that McCartney wrote the song. And that's essentially the process to get the values. And I'll mention that the coefficients ranged from the highest, I believe, was about 1.3. And then the most negative, I believe, was negative 1.2. So again, those positive coefficients correspond to ones that are more in the direction of Paul McCartney, and then the negative ones are the ones that correspond to John Lennon.
I also love logistic regression, although if there's something I don't like about it, it's that it's kind of like vanilla ice cream. I feel the sort of same way about it. Although if there's one criticism, I guess it could be that out of box, it doesn't necessarily deal well with two features that are correlated. So like if this and this means Paul, but this and not something else.
We explored that, yes. So there are ways to incorporate interactions of all of these different features. And that's something that we did as part of the model fitting process. The problem that we were running into is that our training sample consisted of a total of 70 songs, which is really not very many. The problem is that if you start incorporating interactions, which in truth we thought were very relevant, the problem is that once you start going through this automated process of identifying interaction terms that exactly address the issue that you're describing, you very quickly start overfitting the data. So in our view, if we ended up having a much larger corpus of songs to work with, which we're hoping eventually we'll be able to do when we start, spreading out this kind of approach to...
When the Beatles get back together?
Yeah, right. But yeah, maybe expanding more in the direction of like different groups in the 60s, say. Then all of a sudden we have a lot of songs, and then the hope is that we would be able to find interactions. And so this issue of having these correlated features all of a sudden becomes a relevant issue and incorporated into the model.
Yeah, definitely. I'm curious to hear how you think your techniques might generalize. Could it be that some of the features are a little bit hyper-focused to that era? Or might we think that, like you said, the 60s has a lot of common nuance to it? What do you anticipate as you broaden your corpus?
Yeah, so the particular results that we have, along with all of the coefficients for the logistic regression, we view as being very specific to this Lennon-McCartney problem. So I think if we were to apply this approach to distinguish authorship in other settings, probably what we would end up doing is something more in the realm of discriminant kinds of analyses where each author would have essentially its own signature represented by a set of coefficients. So essentially what would happen is if you were to apply this to hundreds of different groups, each group would have its own vector of coefficients. And then if you want to expand it further, you could even go in the direction of saying that those coefficients might even be evolving over time. There are ways to actually include what's called a stochastic process, basically a time series on the coefficients themselves that basically say that in a given year, maybe a group has a particular numerical fingerprint represented by this kind of approach, but then maybe the following year, it'll be a slightly different set of numerical values that won't be too different from the ones from the prior year, but at least there's some statistical model that allows them to evolve over time. And so that's another aspect that we want to incorporate, but we really can until we actually have a lot of data. That's another aspect. Another aspect that eventually we want to be applying all this to, again, using this kind of technology of discriminant type analyses, is once we have these numerical fingerprints for groups, then we could start talking about influence networks. It's commonly understood that John Lennon in 1965, at that point, was being very heavily influenced by Bob Dylan's music. And so there might be a way to say, well, if you start analyzing Bob Dylan's corpus of music using this kind of approach along with all these other musicians, then we can see how far apart the musical fingerprint of Bob Dylan in 65 or 64 maybe, and John Lennon in 65, how far apart they were. And if they're pretty close, then we can actually say something like, look, they're pretty similar. Bob Dylan was writing music a little before John Lennon at that point, and so you can draw some inference about those similarities being at least some level of influence, since we know that John Lennon was listening to Bob Dylan.
So I think the paper would be well received in a statistical group or a machine learning group or musicologists, maybe even rock historians as well. How do you feel about a lawyer getting hold of this and trying to make something of it?
I've heard that question before. So one of the questions that we hear quite a lot in reaction to this work is, can we use our approach to, say, for example, detect plagiarism in music? The issue here is that just about every form of plagiarism in music involves taking sections of a piece of music and then mostly lifting it, inserting it into a new piece of music, essentially copying passages of music from one song into a new song. And our approach doesn't really get at that local level of music. All of the the features that we're picking out of songs tend to be more global about the song, like whether or not the dominant chord occurred in the song. And so you're never really going to be able to say, using our approach, that since all the constituent features are these global measures, and maybe one song or one musician or another musician have very similar sorts of use of these different features, if they're not lining up temporally, it would be a pretty hard case to make, I think, to say that there's plagiarism involved. So I'm not sure our approach lends itself very well to the legal realm.
Yeah, plagiarism's definitely a different problem, I guess I would say. What if we spun it in a slightly different direction, and I, as an enormous Beatles fan, yet someone of questionable morals, wanted to purport that I discovered a secret Beatles song that was recorded and hidden away, and I want to put that fake out there on the internet. How could I use your tool to produce a fake like that?
So the other thing our model cannot do, just talking about all of its limitation, is that it's not a generative model, which is to say that, we can use our model and then just produce a new Beatles song. Now, I will say that this work that I've done with Bach and these Bach chorales is a generative model, which is to say that you just basically let the model run and you have a new Bach chorale. Our approach is not going to be able to produce new songs. What it's essentially going to do is it's going to produce a set of features that is a very bare bones menu of the features that should appear in a song if it is going to sound like the Beatles. So in other words, like all our model will do is, like, if you tell me that you have a song and certain chords or chord progressions or melodic notes are in the song, then all our model will do is it'll tell you what it thinks the probability is that the song is a John Lennon song or a Paul McCartney song. And that's pretty much all it's going to be able to do.
Sure. So if I desire to write in the style of Paul, I could submit iterative drafts and try and push my score up, I imagine.
That's true. You could take any old song and apply our model to it, and it'll tell you the probability that it sounds like a Paul McCartney song or it sounds like a John Lennon song. In fact, one of the things that we did as kind of a fun exercise is my colleague Jason, a number of years ago, wrote a fun song that he and I performed at the launch of the journal where our article appears. As a fun exercise, we actually took his song, which he ended up writing in the style of the Beatles, and we ended up applying our model to it to see whether it sounded more like John or Paul. And it turned out that it sounded incredibly much more like Paul McCartney than it did John Lennon. So you could use the model that way to say, like, if you have a bunch of songs and you think you write songs that sound like the Beatles, but you're not sure whether it's McCartney-like or Lennon-like, you can basically apply our model to it, and then it'll tell you which it is. Of course, you'd still have to go through the manual effort of seeking within each song whether your song has a flat second in it or whether you have a pair of notes on the sixth that occurs. You have to do a bit of manual work to kind of get to that point, though.
Maybe there's a Python library out there that can help me along the way, perhaps, or something.
Yeah, there are apps out there that do the audio deconstruction. So, there are things that probably could help. So why not?
Yeah.
The song that really led to all of this is the song In My Life, which is of disputed authorship. And that's what kind of led us down this path really in the first place.
Yeah, I actually myself don't know that controversy too well. I mean, from the paper, but I didn't know it historically. I don't know if we even call it a controversy, but what is the situation with In the Life?
Yeah, it is actually kind of a controversy. So the song In My Life the song was recorded in October 1965 on Rubber Soul. In the year 2011, Rolling Stone designated it as the 23rd best written song of all time. What is known about the song is that John Lennon wrote the lyrics, but there's a controversy of who wrote the music. Because based on interviews, John Lennon claimed that he wrote most of the music. He exclusively wrote the verse, and then he got a little bit of help from Paul McCartney in the bridge section. So that was Lennon's recollection. And Paul McCartney's recollection was that John Lennon had written the lyrics and then wasn't quite sure about writing the music. And so Paul McCartney basically said to John Lennon, let me just have 10 minutes with this and I'll come up with some music. And he even remembered specifically that he purposely wrote the music to sound like Smokey Robinson and the Miracles. So they were very conflicting recollections. And so that was part of the inspiration of this particular project, to be able to answer the question about that song specifically, because at least among Beatles fans, there is some controversy about, who wrote the song. It turned out what our model said to be almost exactly consistent with John Lennon's recollection, which is to say that our model gives something like an 80% probability that Lennon wrote the verse, and then it's very uncertain. It's like close to maybe 60 to 50% probability that Lennon wrote the bridge section, but with quite a bit of uncertainty about it. And that seems to square much more with Lennon's recounting that the bridge is more collaborative. So it's kind of nice to see that the analyses that correspond to that particular song match a particular recounting that was given by Lennon.
Interesting. Well, I don't know if Paul's going to respond to the work or not, but maybe that part would offend him. Have you heard from his organization at all?
Yeah, some media outlets that took interest in this work did try to contact him, and apparently they're not interested in responding. So we got to the front door and we knocked on it, and then no one answered. But I will say that one of the reasons that might explain why he's not answering is that some of the articles in the popular press that were written about this, especially when we explained that our model gave an 80% probability prediction to Lennon writing In My Life, they basically had headlines like data science shows that Paul McCartney can't remember, or that Paul McCartney lies. They're just like really offensive things, which give them pretty good reason not to respond to us.
Yeah, that's unfortunate. The subtleties of the statistics often don't make it to the headlines for some reason. Well, this has been great. I wanted to just wind up by asking, where you're headed next, either on this line of research or we have talked a little bit about growing the corpus, but in general, what's the future look like for you?
Well, for the musical end, as I mentioned, there are a bunch of different projects that are going to likely come out of this. Some of the work that I do is a lot in the area of games and sports and rating systems. And I have some research contracts with some organizations to basically do better modeling of strategy within games and being able to model career trajectories of athletes. And so that's something that's like the near future for me. But as with most statisticians, we always keep our eyes and ears open and look for interesting projects and see what comes up and then latch on to ones that are interesting.
Well, thanks again for taking the time to come on and share your work.
My pleasure. Thanks for having me on your show.